All right, ever since we introduced the derivative, we stressed that the derivative gives us an instantaneous rate of change, slope of a tangent line. In section 3.6, we're going to just talk a little bit more about derivatives as rates of change. So we know the derivative gives us an instantaneous rate of change. And our first look at this from an application viewpoint is going to be in the area of physics. So here are some basics from the wonderful world of physics. A position function can be given by s of t. The velocity function is given by v of t, and the velocity function v of t is nothing more than s prime of t. So velocity is nothing more than the derivative of the position function. And I think we saw this in an earlier section. The acceleration function, well, that's given by a of t. And the acceleration function a of t is nothing more than the derivative of the velocity function. Or you could think the acceleration function is the second derivative of the position function. And if we ever talk about speed, speed is nothing more than the absolute value of velocity. That is, it's the absolute value of v of t. So the first example we're going to do, this is actually an even-numbered exercise from your text. Here it is, this example. Make sure you get this written down in your notes. A stone's dropped off the edge of a 54-foot cliff on Mars, where the acceleration due to gravity on Mars, it's about 12 feet per second squared. The height in feet of the stone above the ground t seconds after it is dropped is given by the position function s of t equals negative 6t squared plus 54. We are going to determine the velocity of the stone and its speed when it hits the ground. So you know to write this down because I'm going to head off to the chalkboard to work through this one. Some things to keep in mind. We're going to have to determine the derivative of the position function, since the velocity is the derivative of position. And we have to evaluate at the value of t when the stone hits the ground. Now, folks, the stone is going to hit the ground when its height above the ground is 0. So we're going to have to do a little algebra in here. We're going to have to solve the equation s of t equals 0. We'll have to solve that for t. So let's head off to the chalkboard and knock this one out. All right, folks, in this first example, there were a lot of words. Hopefully you wrote all the words down. I just put down the function. The position function is s of t equals negative 6t squared plus 54. And we're supposed to find the velocity and the speed when the stone, when it hits the ground. So let's get the velocity function. So the velocity function, remember, velocity is the derivative of the position function. So the velocity function is the derivative of the position function, which is a negative 12t. So we need to determine the value of t for when the stone actually hits the ground. Well, to find the value of t for when it hits the ground, since s tells us the height above the ground, it hits the ground when s of t is equal to 0. So it hits the ground. We find out the value of t, it hits the ground, by solving that equation. So we take our s of t, set it equal to 0. Let's see, I would subtract 54 from both sides. Divide both sides by 6. Take the square root of both sides. And we realize that the t value of negative 3 doesn't make any sense because t is representing time in seconds. So a negative 3 value for t, I mean, what does that mean? Time travel? And we're not time traveling yet. So the only value of t that makes sense for when the stone hits the ground is t equals 3. So now we can answer the question. V of 3 is negative 12 times 3, which is negative 36. And we should have some units attached here. We're talking about a velocity. So it was negative 36 feet per second. And the speed, well, remember, speed is the absolute value of velocity. So the speed would be 36 feet per second. And that's all there is to this example. So let's head back to the slides and see what's coming at us next. All right, that example wasn't too bad. Let's do another even numbered exercise from your text. So make sure you write this down. Take your time, write it down. It has 5 parts. Here, a stone is thrown vertically upward from the edge of a cliff on Earth, and it has an initial velocity of 19.6 meters per second. And and the height is 24.5 meters above the ground. So the height in meters of the stone above the ground t seconds after it is thrown is given by that position function, s of t equals negative 4.9 t squared plus 19.6 t plus a 24.5. So look at everything we're going to do here. We are going to determine in part A the velocity of the stone after t seconds. We're going to determine in part B when the stone, when it reaches its highest point. Then in part C, we'll determine the height of the stone at the highest point. Part D, we're going to determine when the stone strikes the ground. And then in part E, we're going to determine the velocity that the stone does strike the ground. So folks, we're going to head off to the chalkboard now to work through these 5 parts. All right, hopefully you wrote this one down. A lot of words. We're throwing a stone. We're throwing a stone vertically upward from the edge of a cliff. This is the position function. Part A, we're supposed to get the velocity v of the stone after t seconds. Part B, determine when the stone reaches its highest point. Part C, what is the height of the stone at the highest point? Part D, when does the stone strike the ground? And then part E, with what velocity does the stone strike the ground? So let's knock these out one at a time. So first off, part A. Remember, velocity is the derivative of the position function. So the velocity, take the derivative of the position function and we get negative 9.8t plus 19.6. So that's it for part A. So when does the stone reach its highest point? So, if you take something and you throw it up in the air, while it's going to reach a high point. While it's rising, the velocity is positive. As it's falling to the earth, the velocity is negative. When it's at its highest point, it doesn't have velocity. Its velocity is 0. So that means in part B, when does the stone reach its highest point? It reaches its highest point when velocity is 0. In general, when velocity is 0. So we take our velocity function, set it equal to 0, and solve for t, and we'll get t is equal to 2 seconds. So it reaches its highest point after 2 seconds. Part C, what is the highest point? Well, that's nothing more than evaluating the position function at 2. The position function tells us the position of the stone. So we toss 2 into the position function. That tells us what its highest point is. So if you put 2 in for the t's, let's see, I used my calculator and I got 44.1, and the units were meters, 44.1 meters. Part D, when does the stone strike the ground? Well, it strikes the ground when its distance above the ground is 0. So we take the position function and set it equal to 0. And solve for t. All right, I used the quadratic formula here because I see messy looking decimals. And when I used the quadratic formula, I ended up finding 2 solutions to this equation, -1 and 5. Of course, the -1 doesn't make sense because we do not time travel. So t is equal to 5. So part D, when does it hit the ground? It hits the ground 5 seconds after it was tossed into the air. Part E, with what velocity does it hit the ground? Well, part E is just nothing more than evaluating the velocity function at 5. So here's your velocity function. Toss 5 in for the t, and I get -29.4, and then the units are meters per second. There should be units attached to that. All right, folks, let's head back to the slides and see what more we can do with derivatives as rates of change. Let's look at another example after just doing a couple of physics examples. Let's do a non-physics example. The population of the state of Washington can be modeled by that function on the interval 0 is less than or equal to t is less than or equal to 6. And in this situation, t is the number of years since 2010, and p of t, well, that's the population in millions. In part A, we are going to evaluate p prime of 1 and interpret. And then in part B, we'll evaluate p prime of 6 and interpret. So as always, folks, get this written in your notes because I'm heading off to the chalkboard to work through it. All right, in this example, we were given this function, and this function was modeling the population of the state of Washington, and t is the number of years since 2010, and p of t, well, that's the population in millions. So part A, evaluate p prime of 1 and interpret. Well, in order to evaluate p prime of 1, we have to first get p prime of t. We have to get the derivative of the population function. So p prime of t equals, let's see, 0.0078 times 2. That's 0.0156 t plus 0.028. So there's the derivative. We can now evaluate the derivative at 1. So 1 comes in for the t, and we get 0.0436. So what does this mean? Well, remember, t is the number of years since 2000. So a t value of 1 would be 1 year since 2010. So a t value of 1 would be 1 year since 2010. That would be the year 2011. So in 2011, the population of Washington was, since this is a positive number, I use the word increasing at a rate of 0.0436 million, and it's a rate, so we have to have units attached. It's million per year. So hey, why don't you do part B? You already have the derivative, so why don't you evaluate p prime of 6 and write down what you think the interpretation is. So pause the video, do that real quick, and then restart the video, and I'll be here at the board to make sure you're correct. All right, folks, I have p prime of 6 to be 0.1216. 6. So 6 years since 2010. 6 years since 2010 would be 2016. So my interpretation is, in 2016, the population of Washington was increasing at a rate of 0.1216 million per year. All right, let's head back to the slides and see what's waiting for us. All right, let's do one more even numbered exercise from your textbook where we're actually going to compare velocities. So here's the example, take your time, write this down. 2 stones are thrown vertically upward. Each has an initial velocity of 48 feet per second at time t equals 0. That's what it means for an initial velocity. Now, one stone is thrown from the edge of a bridge that is 32 feet above the ground. The other stone, it's thrown from ground level. Now, the height above the ground of the stone that's thrown from the bridge after t seconds is given by f of t equals negative 16t squared plus 48t plus 32, whereas the height of the stone thrown from the ground after t seconds is given by g of t equals negative 16t squared plus 48t. In part A, we are going to show that the stones reach their high points at the same time. Part B will determine how much higher the stone thrown from the bridge will go than the stone thrown from the ground. Then in part C, we'll determine when the stones strike the ground and with what velocities. So have this example written down because we're heading off to the chalkboard to work through it. All right, in this one there were a lot of words. There were stones being thrown vertically upward with the same initial velocity, 48 feet per second. One stone was thrown from a bridge and one was thrown from the ground. This was the position function for the bridge. That's the position function for the ground. So in part A, show that the stones reach their high points at the same time. So remember, a high point, the velocity would be 0. So for part A, we need to get the derivative of the position function, because derivative of position function gives us velocity. So for the bridge, the derivative is negative 32t plus 48. For the stone that was thrown from the ground, the derivative is negative 32t plus 48. Identical velocity functions. So we can see they are the same. We can see that we have the same velocity functions, so it will reach its high point at the same time. So now remember, high point velocity is 0. So I take the the velocity, set it equal to 0. I solve for t and I end up getting t as 3/2 or 1.5. So for the stone thrown from the bridge or the stone thrown from the ground, they both reach the high point after 1.5 seconds. Okay, part B, how much higher does the stone throw from the bridge go than the stone thrown from the ground? So here's what we need to do in part B. The stone thrown from the bridge, this is the position function. We need to evaluate it at 3/2. Or, you know what? Instead of the fraction, why don't we do 1.5? So we put 1.5 in for the t's, and I get 68. So that means the stone thrown from the bridge has a high point of 68 feet. Now the stone thrown from the ground, it reaches its high point after 1.5 seconds. To see how high it goes, we put 1.5 into the function for t, and I get 36. Both of these are in feet. I should write that down. So how much higher did the stone throw from the bridge go than the stone thrown from the ground? Well, a simple subtraction tells us that it went 32 feet higher. Okay, now part C. When do the stones strike the ground and with what velocities? All right, so we need to solve f of t equals 0 and g of t equals 0. This tells us when the stone thrown from the bridge hits the ground. This tells us when the stone thrown from the ground, comes back to the ground. So, you know what? Let me solve this one here real quick. You have a negative 16t squared plus a 48t equals 0. If you factor out a negative 16t, you're left with a t minus 3. So you get t is 0, t is 3. That one doesn't make any sense because, if no time has passed, it's still at ground level. So it goes up and it comes back down and hits the ground at 3 seconds. So what's the velocity with which it hits the ground? Well, evaluate the derivative at 3. And you evaluate the derivative at 3 and you get negative 48 feet per second. So the stone thrown from the ground hits the ground 3 seconds after it was thrown, and it hits the ground with a velocity of negative 48 feet per second. Okay, here for the bridge. Alright, so let me tell you folks, I'm going to crank this through the quadratic formula. Since that's algebra, I'll let you do that on your own, cranking it through the quadratic formula. And then I'm going to approximate what these answers are. So when I crank this through the quadratic formula, I get a t value to be approximately negative 0.562 and a t value of about 3.562. Obviously, this one is meaningless because we don't time travel. So what's the velocity? We know how long. So the stone that's thrown from the bridge hits the ground after about 3.562 seconds after it was thrown. The velocity with which it hits the ground is found by evaluating the derivative at 3.562. So here's the derivative evaluated at 3.562, and here I get negative 65.984 feet per second. Folks, that's it for section 3.6. So now you can do the exercises in section 3.6, and thanks for watching.